Welcome to another episode of Code for Thought. In this episode, I have the pleasure of talking to Veronika Cheplygina from Copenhagen in Denmark. Her background is in machine learning, and part of our discussion focuses on AI and machine learning in the field of medicine and in particular medical imaging. Machine learning, of course, has been studied and used in medicine for some time, way before the current hype. And in 2022, for instance, just weeks before the pandemic, I attended a 2-day seminar in London on how machine learning can help with diagnostics, drug discovery, patient management, and other areas in healthcare. In 2019, a medical scientist and cardiologist in the US called Eric Topol published a book called Deep Medicine, which he subtitled How Artificial Intelligence Can Make Healthcare Human Again. And just weeks before our interview in summer 2023, I read an article how a machine learning application was able to find abnormalities better and more efficiently than radiologists. But in order to assess how valuable machine learning algorithms or applications are to patients and health professionals, we need to look behind the headlines and recognize what their limitations are. We need to think how we select cases and data and how open we are not only about our research successes, but also our failures and misses. These are all questions that Veronika has been dealing with throughout her career, as you will hear from our conversation. Veronika has also been refreshingly open about her frustrations with some aspects of academic life. And let me just mention publish or perish here. And she brings a badly needed realism to the field of machine learning and AI. So here now, my conversation with Veronika. Hello Veronika, thank you very much for joining me today. Perhaps you can quickly introduce yourself.
Sure, thanks for the invite. My name is Veronika. I'm an associate professor at IT University of Copenhagen in the Department of Computer Science, and my field of research is machine learning in medical imaging.
Excellent. So how did you get into that?
I studied computer science in Delft in the Netherlands, and I think towards the end of my master's we had a subject then called pattern recognition, which introduced the basics of this. And one thing led to another, and I did a PhD project in pattern recognition or machine learning. That was more about different types of data and a particular methodology, more focusing on learning from smaller data sets for which not a lot of labels are available. And then as one of the projects within that, I came across medical imaging dataset about the recognition of the lung disease COPD. So that was one of the chapters in my PhD project. And from then on, basically, that was the area I focused on more. First in the Netherlands and now in Denmark.
All right, exactly, because you're in Copenhagen, aren't you?
Yes.
Since when, if I may ask?
February 2021. So I moved at the height of the pandemic, I think.
Okay, that must have been quite something. The idea of dealing with machine learning data where there's a limited data set, that is quite interesting. What kind of technologies are you using to make sense of data sets which are small in size or limited, which is something that might actually happen in medical imaging, doesn't it?
That is for sure true. I mean, I think I want to preface this with that all data sets are limited in size, and that just purely looking at the size of the data set does not always tell us if it will be enough for what we want to use it for. But for example, comparing medical imaging to other visual recognition tasks like cats and dogs and cars and pedestrians, medical data sets are definitely smaller in size. And it's only in part because, rare diseases, sometimes the conditions can be very widespread, but for various reasons, the data is not available for researchers because it wasn't collected for that purpose, because of privacy issues, and so on. And on the other hand, there's also the problem of associating the images or the scans that might have been made to diagnoses or labels that you want to predict for these images. So if you want to outline different organs in the image, you would need such outlines from experts, and that's very time consuming to make as well.
For these kind of testing and training sets, it's quite time consuming to produce them, isn't it?
Yes, so there are various techniques that try to learn from more easily available labels. So, for example, rather than having a scan with locations of abnormalities, you would only have a label that some abnormalities are present somewhere in the scan. For example, such a label could be extracted from a radiology report that somebody had written while quickly looking through the image, but then you wouldn't have the location information.
So we hear a lot about machine learning and AI. In what areas is AI or machine learning used? Could you name a few examples where this is being deployed in clinical practice, I mean?
Actually, recently I was looking at a list of FDA approved software. There are many medical specialties, so in radiology and so on. I think a very common use case is trying to measure different organs or abnormalities.
Hmm.
So for this, you would need the software to outline them and perhaps compare the size to, for example, you could compare the size of a tumor to a scan from the same patient several months ago. I think diagnostics is less frequent in like actually implemented in the software, but there's quite a lot of research being done on it. The research that makes it to the headlines is often about, we correctly predicted 95% of cases of people who have cancer. It sounds more exciting than we have measured how big your liver is accurate to the millimeter.
Well, it's exactly that hype that I want to talk about a little bit because, as you quite rightly say, there has been quite a few articles in the press. And recently, while we're recording, that's in August 2023, a few weeks earlier, there was in the British press and also in other news outlets that claimed that breast cancer detection has been better than being used by two radiologists or two experts in the field. So AI and machine learning outpaced the experts. So the temptation is then to think that, well, what do we need experts for if machine learning and AI is doing a better job? What would you say to that?
In many of these, I have not read this article in detail, but in many of articles reporting something being on par or better than experts, I think the measure being considered is not quite mirroring what the experts actually do as a whole in their job. So it might focus on a specific thing like detecting abnormalities, for example. I do see in this article that this is a randomized controlled trial, which is rare, but it's good that this is being done to actually test how things work in practice compared to no AI being used. But it's still the question for me whether screening with, the metrics that they measure in this trial, whether that equates to the job of a radiologist.
So the radiologist is not just looking at images, of course. There's the interpretation of the images and there's the whole patient care. So it's only a part of what they actually do. Is that what you're saying?
Yes, so it's not the, how correctly things were recognized is not the only thing. Of course, it's not like it would be a good development if the results show, okay, when radiologists work together with this technology, it improves the survivability of the patients, or it has reduced the time, so we can treat more patients in the same time, and so on. But I don't know if these metrics are being measured.
You are currently part of a project at the I'm reading this out now, Data Intensive Systems and Applications Organization, or I think it's called DASIA or DASIA.
We said Dacia.
Dasha, okay. And your project involves pattern recognition in medicine, which is just what we've talked about. But could you explain and describe this project in more detail and what you're doing there?
So the Data Intensive Systems and Application group, this is a group which is part of the Department of Computer Science that I'm in. Well, within this, people are focusing on different topics, some of which have nothing to do with medicine. And I have various projects related to that. In one, we're looking at transfer learning. That's one technique that tries to improve how robustly we can train networks if our target task doesn't have a lot of data. So the idea is we first train on some larger data sets to try to learn more general things, for example, more general things about how images are structured. And then we train more specifically on the task of interest, for example, breast cancer screening.
When it comes to transfer, so is then the transfer that we try to identify common patterns, say, in images at a very large data set, and then hoping or assuming that some of these principles or patterns can be transferred over to other images. Is that the principle of transfer
Yes,
networks?
exactly. So actually, a quite popular thing to do now is to do this initial training, the pre-training on ImageNet, which is a data set of cars, cats, dogs, etc.,
Hmm.
and then fine-tune on medical tasks. This is a quite common use case which works relatively well.
Which is a bit counterintuitive, isn't it? Because you take, as you say, cats, dogs, and cars, and there's these big image libraries available. And then you're transferring that to medical images, which obviously are very different. So, why do you think this transfer works?
I think it learns that things for our vision, which we use both when we look at the natural world and medical images, so things like edges, blobs, circles, that these are important
Mhm.
structures, and that it's good to pay attention to those. There's actually also recently been a dataset released called RAD ImageNet, and the idea there is to make a similar size dataset but only of radiological images
Mhm.
to use for pre-training. And they report that they get better results on their target tasks. We've tried it on a set of slightly different tasks, and we wouldn't say get better results, but they're quite comparable. So I
Mhm.
think in the end, the information that's extracted or transferred, it does not hurt too much that one of them has entirely different images, but the images have somehow similar structures.
So, how would you ascertain or assess the performance of the machine learning? I'm just following up from what you said. So, you have these big image sets for transfer learning where you start with cats and dogs and you transfer some of the output or the outcomes from that to data sets that are medical images. And then you can, as you just said, there's a radiological image database which claims to be better, and you're trying to verify that. What are the kind of testing criteria and how does that work?
Yeah, so usually there are some metrics on the test set that we can measure, okay, how well is the network trained with this one rather than with that one? How well are they in distinguishing the different pathologies? So what is measured is often area under the receiver operating characteristic. And that's basically, it's not like accuracy, like how many did it get correct, but rather how often is the algorithm classifying something, a positive sample, as more positive than a negative sample. Essentially, it's like looking at all the combinations of positives and negatives and seeing if it orders them correctly,
Okay.
which is a slightly different measure than just saying, did it say yes or no?
Okay. Is there a better way to get a more nuanced output from that?
It is better in some ways, and I think also potentially misleading in some other ways, but it is what is very often used for medical images.
How do you see that machine learning and artificial intelligence is going to be deployed in medicine in future from your perspective?
I mean, I think definitely as a software to support tasks and reduce time. So, for example, in scans, highlighting areas of concern, prioritizing which scans should be seen by which or how many radiologists. So, if there's certain cases or cases that might be more urgent, making the best of the resources available. I do see that this would be done in practice. I don't want to think about too many doom scenarios of like everything that could go wrong actually going wrong. If things work like this and people are aware of the limitations of the software they're using, that would be a good scenario.
I think that's quite a good description because what you're saying effectively is that we use it as a tool for what I think is called triaging. So you have number of patients coming in, and if the system flags up that there might be a problem, then a radiologist could look at it and say, yeah, there is, or no, there isn't. But for the most cases, hopefully, there won't be a problem and it's clear cut, and the AI algorithm and machine learning makes the right decision of saying, okay, it's safe to say, yes, there is something, or no, there is nothing.
I think potentially the distinction between there's definitely nothing and somebody should look at it, this could be a dangerous decision to make. But if we
Mm,
already have a list of patients who clearly need to be looked at, potentially there could be like more rare cases there that could be looked at somebody with a specific specialty or
okay.
by more radiologists in general. So I think this like ruling out, yeah, there's potentially more problems there, like who's responsible if you missed something.
Okay, so it's even narrower defined. We already have a list of patients that we need to look into, and it could help us pointing them to specialists if need be.
The way that all of these processes fit together is not exactly within my expertise. But it's not that all of us, get MR and CT scans every year, that we could just run everything in case somebody has developed something, because we're not getting those scans. So somehow the scans which are at the hospital are there for a reason already.
You're not doing them for nothing, basically. You go in there, you have a brain scan because somebody says, well, we're not quite sure. You need to have a brain scan to identify
Yes,
something.
there's usually some other reason that the scan was made. Of course, it's possible if you have an unrelated accident that you also had a scan. So maybe there's a use case that if that happened, that also something else was detected. I also think that if you come to the hospital for a specific problem A, the scans that will be ordered might be different than if they're definitely looking for specific types of tumors or something else. You're only getting the scans that we know that you might need.
Yeah, it makes sense because you're actually making a choice right there, saying that you're getting a brain scan because somebody thinks you might have a problem in your head somewhere, rather than say your liver, which would be a completely different. I mean, to put it crudely, but sometimes even in the same body region, there might be different scanning techniques depending on what it is you're actually looking for.
Yeah, for sure. If you had an accident or something is just embedded in your skull, you don't need the same kind of scanning as to look for sort of microbleeds inside the brain.
Yeah.
It would be a different protocol.
We already touched a little bit on this, the possibility of systems actually failing. And very often we read about the successes of AI and machine learning. We don't really read so much about the failures or the limitations. I saw your blog post, and I think you've written on that subject of failures and facing up to them quite openly. So, how important is it that we report our failures, not our successes? And are we doing that enough, in your view?
I think with machine learning, it's a bit dangerous because something might look successful but not in fact be. So it is possible to create a scenario where, for example, the detection rate, like these metrics that I talked about of cancer, is very high in a study, but that it actually fails if it were to be deployed on the general population with or without the disease. So one example how this can happen is if there's some kind of shortcut in the data which is correlated to the diagnosis, the algorithm might learn the shortcut rather than the actual diagnosis. Say you would have a study with scans from both a specialized cancer research center and a regular hospital, which use slightly different scanners. If it happens to be that the specialized cancer hospital has more severe cases of cancer, the characteristics of the scanner are a shortcut for guessing more often correctly that indeed this patient has cancer.
Okay.
It's like a confounder between the scan and the diagnosis. So even though it's true that more patients at that special cancer research center have cancer, that shouldn't be the characteristic that's important for recognizing cancer in general.
Okay, so you're introducing basically a bias. It kind of weighs more towards the direction of this particular type of cancer because in that hospital you get a lot of that. Is that what
Yes.
it is?
But this might not be obvious at all to you from the data that you use for development, for example.
Is that something that you see often, or is that something that you see sometimes in practice? Is that being reported then?
I think recently some studies have been coming out showing how to uncover these type of shortcuts. There's definitely have been some examples in chest x-rays. So for example, there's some artifacts like, for example, pacemakers or chest drains, which also are a confounder to what we're trying to diagnose. So they become important features like, oh, you were already ill, so I see that there's a pacemaker and a chest drain. It's also more likely that you have this diagnosis. Of course, the algorithm doesn't reason this way. It picks up on, well, some lines going across here are frequently correlated with a positive diagnosis. Other examples are in skin lesion in dermatology. A known shortcut that has been demonstrated now in several datasets is if a dermatologist had put pen marks next to the lesion before taking a picture.
Yeah.
This usually means that the dermatologist is already suspecting something, and we can actually demonstrate that pen marks around the lesion is something that helps the algorithm correctly guess that it's a cancerous skin lesion. But this is because it's a visual feature that's correlated to the diagnosis, so it gets learned.
So basically, it reinforces the diagnosis. It's almost like a circular argument, isn't it?
Yes.
So you're trying to use the algorithm to find a particular type of skin lesion or diagnose it, but then you already suspect it and by marking it, and therefore the algorithm is more likely of finding it than without these markers.
Yes. So in a different situation where you would like to use this algorithm, the dermatologists are not using these pen marks at all. It would do worse on detecting melanoma or other problems. It would do worse than reported in the original study.
Do we actually get this as a public to read about it? These kind of, I wouldn't call them failures. I would call them more or less like constraints or limitations. But how important is it that actually that we are made aware of that in your view?
The research articles are definitely out there. I think for software that has been approved by FDA and similar authorities, there's at least some reporting of how it was tested. But what I'm describing, there's not really a standardized test procedure to try to test all these artifacts and edge cases. There isn't one website you can just go to and see all the results of how good is different software that your hospital might use. How much should you trust that? And I think if you want to look into it, you can find some information and try to connect it to research that exists, but it's not, I think, readily available to digest to like inform people.
I'd like to talk more about your blog because you've written a blog which covers failures in science in general, not just machine learning, which is what we just discussed. So, what made you write this blog and what do you hope people take away from that?
Yeah, I think how it came to be and what it became, it sort of evolved a little bit. It started happening when I was starting to be disillusioned with academic research. And I think I just wrote my experiences down, which is, I guess, what you do in a blog. But then people started picking that up, and sort of that developed into its own thing of me interviewing a few more people and also thinking more generally how this relates to research and science. I have to say, I haven't really done anything on this topic since I think I moved to Copenhagen because academia started treating me a little bit better,
Better.
and I
Okay.
I got comfortable with focusing on my research topic and not the meta topic of potentially leaving research.
What was it that got you disillusioned with academia in the first place?
I mean, then very direct things I was experiencing is that publication was very much related to introducing novel methodology that would show state-of-the-art results. And since that was the metric that needed to be optimized by Goodhart's law, people optimized for it, creating more and more complicated methods that appeared to have better performance, but actually, probably weren't robust for different use cases like this. I felt I didn't want to spend my time on engineering something just for the purpose of publication, but something that wouldn't actually work well. And I don't mean that it wouldn't be used in practice, but it didn't feel like adding something to the body of knowledge that we have.
Okay, so it's the kind of publish or perish, right? So you publish, or as an academic, then you sink. You have to publish, basically.
Yeah, and so I mean, I think it's fine to publish, but the places where I was meant to publish, many of them focused on the wrong reasons, I think. At that time, I also started applying for research funding, and there was a little bit of the same. Rather than your research idea, what counted was your CV and where you have published.
Right, okay.
And not actually what the publication, like what did this publication contribute to the research field.
Well, that's interesting because I think that it's something that disturbs, shall we say, a lot of scientists when we talk about publishing and the merits of publishing. And why you put so much emphasis on publish in terms of impact factors, because that's what you're saying, that we focus on where you publish and if you publish, but not exactly what. And what new does it bring to the table? Is that what you're saying?
Yes, and this new can be understanding of something or, connecting different topics that were not yet connected before. In my specific field, it was frustrating that the only new thing you could bring was yet another algorithm, but there are already so many. And we don't really have good metrics for distinguishing them because the on the data sets that we have, the performances are all so close that if we translate that to, like, what would it mean in practice? Will more lives have been saved if this is used? I mean, I think not, because I think these differences are only numerical from sort of running the experiments multiple times, and not necessarily because the algorithm is actually better at something.
And now that you haven't published since you moved to Copenhagen, has the situation then improved, or has the pressure come off a little bit from your point of view? I mean, published in the sense of not publishing on your blog.
Yeah, indeed. I think already when interviewing for this job, I think I expressed what I think about my field and what kind of things I don't want to do. And I was hired, so I guess that we're in alignment.
At least at that point.
There, I think it's considered to do this kind of, for example, work with surveys which connect different literature, or work that uncovers what things might be going wrong in already existing methodology. Yeah, I feel that that's appreciated, so that's what I've been focusing on.
So finally, what's next for you?
I'm hoping to do a project on, with this more meta research question on how do researchers, maybe in machine learning, how do they select what kind of data sets they're going to work on? I have a suspicion that some data sets or applications might be over or underrepresented compared to the potential impact of solving that problem.
What do you mean by that?
So there might be some diseases for which there are data sets where there's a lot of publications using those data sets.
Mm.
But on the other hand, there might be some diseases for which there's just no data set, and then nobody's working on it.
Oh, right,
So there's
okay.
a kind of over and under representation on what people choose to work on because of circumstances like data availability, or, what the grant funder wanted. Which research was easier to get published?
Which brings us nicely back to the question of publish or perish. Okay, well, thank you very much for your time, Veronika. And I think there's a lot to be done with machine learning in medicine. And it all sounds very exciting, but we should also be a little bit aware of the hype and the limitations,
For sure.
shouldn't we? Okay, thank you very much again, and all the best to you.
Thank you.
If you are interested in Veronika's work, I included some links in the episode notes. And next in line will be another bite-sized RSE episode on Thursday, and this time on the subject of easy build for high-performance computing. So stay tuned. Oh, time's up. See you next time. But before I forget, this podcast is covered by the Creative Commons license. See ya.